In today's lecture, we are going to discuss dimension reduction. First, let's define dimension. In analytics, dimension usually refers to the number of variables. In most cases, we are only referring to the number of predictor variables. For example, if a dataset has 2 variables, then it is a 2-dimensional dataset. For a dataset with 10 variables, it is referred to as a 10-dimensional dataset. High-dimensional datasets are datasets with a large number of variables. The higher the dimensionality of the data, the more complex the dataset. So today's topic, dimension reduction, deals with how to reduce the number of variables and at the same time the complexity of the dataset. In analytics, we constantly struggle with the trade-off between variance and bias. Variance is the result of overfitting, which happens when we have too many variables in our data model. Bias is the result of underfitting, which means that not all relevant variables have been included in our model. Today we are going to focus on the first problem. How do we deal with data sets with too many variables? In the big data environment that we are in today, it is not uncommon to see data sets with dozens or even hundreds of variables. Sometimes, even when the original data set may be small, data transformation can cause many derived variables to emerge. These datasets are often problematic to handle. Therefore, dimension reduction is often a necessary step in data mining to pre-process the data before supervised or unsupervised data mining techniques can be applied. There are usually 2 goals of dimension reduction. First, obviously, we want to reduce the number of predictor variables to a more manageable set, hence the name dimension reduction. Second, we want to make sure that the reduced set of predictor variables are uncorrelated or somewhat uncorrelated. Correlation between variables suggests that there is information redundancy between variables. Uncorrelated variables suggest that each variable offers information that is not currently present in other variables, which is a desirable attribute of datasets. In this lecture, we will discuss various strategies for achieving these 2 goals of dimension reduction. First, let's have a philosophical discussion about whether having large datasets is a blessing or curse. Most people would think having big data is a blessing. After all, the field of business analytics is only possible and popular because of the availability of big data today. But big data also adds tremendous complexity to analysis. Therefore, we need to understand the pros and cons of big data sets. Let's start with the pros. First, more data often means more information. With large data sets, the analyst has a better chance of discovering something interesting. For example, the association between purchasing beer and diapers would not be found if it weren't for the big data. However, not all big data offer more information. We will talk more about this topic later. Second, large data sets make it easier to handle missing values. With large enough datasets, we can afford to omit the observations with missing values without losing much of the datasets. Large datasets also make data partitioning possible, which is a requirement for supervised data mining techniques. Third, large datasets with many variables reduce the chance of underfitting, which happens when relevant predictor variables are omitted from the analysis. Having more predictor variables often helps the model to fit the data more closely. Of course, the flip side of this is that having too many predictor variables can lead to overfitting, which is a common problem in predictive modeling. Now let's discuss the cons of large data sets. When we have many variables, inevitably, some variables are going to be highly correlated with other variables. Variables that are highly correlated create information overlap or redundancy. In other words, it increases the data size without increasing the information in the data. A consequence of information redundancy is model instability. Small changes in data values might result in radically different models. For example, in regression analysis, highly correlated variables can cause the multi-collinearity problem, which leads to model instability. Second, too many predictor variables can lead to overfitting. Overfitting occurs when the model fits the training data too well but cannot generalize to unseen datasets, such as the validation dataset. This is because the variables that are irrelevant to the underlying patterns and the relationships of the data have been included in the model to fit the noises of the training dataset. Finally, high-dimensional data cause the curse of dimensionality or sparseness of data. One consequence of the high-dimensional data is that it will take a lot of data points to fill the multi-dimensional space so that the data points are not too far apart from each other. Here is one way to visualize the curse of dimensionality. Let's say that you have a straight line that's 100 yards long. And you drop a penny somewhere on this line. How long do you think it would take you to find that penny? Well, not very long, right? Probably a couple minutes the most. Now let's say that you have a square that is 100 yards on each side. And you drop a penny somewhere inside the square. How long do you think it will take you to find the penny? Now imagine a 100 yard by 100 yard square. That is almost 2 football fields put together. It will certainly take you much longer to find that penny, maybe hours. Now let's imagine a 100 yard by 100 yard and by 100 yard cube. And you drop a penny somewhere in that cube. Now the space is like a 30-story building, the size of 2 football fields. It is going to take you days or even weeks to find that penny. So as you can see, when you go from 1 to 2, then to 3-dimensional spaces, the space increases exponentially. It will take a lot more data points to fill the multi-dimensional space so that the data are not too sparse. As our discussion shows, large data sets can sometimes be more hassle than they are worth. Learning to handle data sets with a large number of variables is an important skill in analytics. In the next few slides, we are going to discuss the various strategies for reducing the dimensionality of data without severe loss of information. In this lecture, We're going to discuss 4 techniques for dimension reduction. When faced with a dataset with many variables, you should implement these techniques in the same order as they are introduced. We start with incorporating domain knowledge to eliminate the unnecessary variables. Then use summary statistics to help detect any information redundancy. Then we use data transformation strategies to reduce categories for categorical variables. And finally, as the last resort, we use dimension reduction analytics techniques. As with many other situations in analytics, jumping right into computerized analytics techniques is tempting, but it's the wrong move to make. Let's talk about our first strategy, incorporating domain knowledge. The first step in dimension reduction is to remove irrelevant variables from the dataset. And that is best achieved through domain knowledge about the unique business problem that you are trying to solve. A subject area expert can usually tell you if you are looking for answers in the wrong places. Get the help of an expert if you are unfamiliar with the subject area to tell you if the variables are relevant to the problem or if they are useless to answering your questions. Sometimes certain variables may not be available to measure, cannot be measured accurately, or may be too costly to measure. Then including these variables in your model would not be very helpful, because the model cannot be applied to future cases where these variables are not present or measured accurately. It is also not helpful if a variable is a trailing indicator rather than a leading indicator, if your goal is to develop predictive models. For example, in a project where a hospital is trying to develop a predictive model for estimating the cost of ER visits for patients. One of the variables from the historical data, called the number of medical exams taken at ER, has a very high correlation with the cost of ER visits. However, the number of exams the patient takes at ER is only known either during the ER visit or after the ER visit. So it is really not a leading indicator, but more like a trailing indicator. So it wouldn't be suitable to be included in the predictive model. Therefore, variables like that should be eliminated before modeling to reduce data dimension and at the same time to avoid problems such as information leakage, which means that the information about the target variable has been leaked into one or more predictor variables. After the data dimensions have been reduced by incorporating domain knowledge, the analyst can use the second strategy, which is to use the summary statistics to further reduce data dimension by removing information redundancy. A few common summary statistics are very useful. For example, the mean or average, the median, minimum, maximum, count, or count blank. These functions allow the analyst to understand the shape of the data, whether there are a large number of missing values, whether the data is normally distributed or skewed, and whether there are extreme outliers in the dataset. Problematic variables can be removed from the dataset. Correlation, which looks at the mutual relationship between two variables, can also be used on numeric variables to identify information redundancy. When two variables are highly correlated, either positively or negatively, there is a high degree of information redundancy between them, meaning that the information in one variable may be repeated in another variable. Then you need to consider whether it makes sense to include all these variables, because you are simply having a lot of variables that are telling you the same thing. That is why we say that sometimes when there are a lot of data, it may not have a lot of information. For example, if you look at the correlation matrix at the bottom left of this slide, you would notice that all of these items are highly positively correlated because of the close to 1 correlation coefficients. The items are things that people think are important collected from a survey. The correlation matrix shows that how a person feels about one of these things is consistent with how the same person feels about other things in the list. The implication of this is that maybe we only need to ask about one item instead of asking about all 9 items in order to understand what a person thinks is important. For categorical variables, correlation analysis would not work, but we can use something called contingency tables to reveal the same information. For example, the bottom right side of this slide shows a contingency table that reports 115 people's favorite games and favorite snacks. For example, 10 people claim that their favorite game is poker and the favorite snack is pizza rolls. So, can you see a relationship between favorite game and the favorite snack? Well, it seems so in this table. For example, poker players overwhelmingly do not choose chips and dip as their favorite snack, whereas chips and dip is the favorite snack of almost half of the Trivial Pursuit players. Whether the relationship is significant or not would require more tests, such as the chi-square test, but we can see that there is some relationship even with our naked eyes. But also, we can see that the relationship is not absolute, meaning that knowing someone's favorite game does not always give you the correct answer to the person's favorite snack. This suggests that while there is some information overlap between the two variables, there is still information that is proprietary to each variable. We can also use pivot table to look at the relationship between categorical variables and numeric variables. For example, use the pivot table to show houses with various number of bedrooms, which is a categorical variable, and their average house values, which is a numeric variable, to see if the number of bedrooms makes a difference in terms of house value. In addition to analyzing these summary statistics between predictor variables to detect information overlap, you can also use the same techniques to detect relevancy between predictor variables and the target variable. As you can see, using summary statistics provides another level of scrutiny for information redundancy and relevance in the effort to reduce data dimensions. The third strategy for dimension reduction lies in the process of data transformation. One process that tends to add many variables to the dataset is the process of converting categorical variables into more usable forms in analysis. A common technique for transforming categorical variables is to create n-1 dummy variables or binary variables, n being the number of categories. For example, if the categorical variable is day of the week, then it is transformed into 7-1 or 6 dummy variables. But if the categorical variable is month, then it is transformed into 12-1 or 11 dummy variables. As you can see, this process significantly increases the number of variables or data dimensions. When dealing with a categorical variable that represents some type of ranking or hierarchy, it may make sense to convert them into category scores instead of dummy variables. For example, converting age groups into 1, 2, 3, 4 representing ages from the lowest to the highest, or converting satisfaction levels to 1 to 7, representing the level of satisfaction from the lowest to the highest. This conversion only requires one variable to represent the categorical variable, therefore does not add any data dimension to the dataset. When using dummy variables is inevitable, we can still try to minimize the number of dummy variables to create. For example, some categories may contain very few observations, and creating a dummy variable for these categories separately will only dilute the data unnecessarily. You can combine these categories and create a dummy variable called others to represent whether the observation belongs to one of these rare categories. Sometimes, certain categories may behave in the same way. For example, sales of products may remain relatively stable throughout the year, but then experience a spike during the holiday season and a steep decline right after the holidays. Then instead of creating dummy variables for all the months that tend to behave similarly can be grouped into one category called the regular month, and have other two categories such as holiday month and the months after the holiday to represent three different sales patterns throughout the year. Again, to do this successfully, the analyst needs to use a combination of domain knowledge and summary statistics to identify the best ways to reduce dimensions. There are also specialized data mining techniques that are less affected by data dimensions. For example, one of the data mining techniques that we discuss in this class is naive Bayes, which is a classification technique for categorical variables only. This technique does not require categorical variables to be transformed into dummy variables, thus would not increase the dimensionality of the dataset. Another technique, decision trees, which we will discuss in this class as well, is a classification and prediction technique that performs automatic variable selection. Therefore, is less affected by high dimensionality of the data. Nevertheless, including variables that are highly correlated or irrelevant to the business objectives still can negatively impact the quality of decision tree models. Therefore, using these techniques would not be an excuse for bypassing the dimension reduction step in analysis. Only after you have exhausted all the dimension reduction options and the strategies that we have discussed so far, should you consider automated dimension reduction analytics techniques to further reduce data dimensions. Although these are powerful techniques that can significantly reduce data dimensions, they are also completely data-driven. Therefore, do not take into consideration the business context of the data. Blindly relying on these techniques for dimension reduction would be a mistake and leads to poor predictive models. Remember the old saying, garbage in, garbage out? You need to make sure that the data set you feed into these techniques are high quality to start with. Otherwise, the reduced data set you get from these techniques are going to be useless. These automated dimension reduction techniques are considered unsupervised data mining because no target variables are needed. Only predictor variables would be analyzed using these techniques. They are used as a part of data preprocessing to prepare the data for subsequent analysis, both supervised and unsupervised. These techniques include principal component analysis, or PCA, factor analysis, variable clustering, and correspondence analysis, which is the version of principal component analysis for categorical variables. In this lecture, we are going to focus on PCA only. Fact analysis is an extension of PCA that helps aggregate variables into constructs. Variable clustering technique groups variables into clusters and use representative variables to represent each cluster. All of these techniques are to some extent based on PCA. Therefore, we will focus on PCA in this lecture. And you can explore the other techniques on your own once you have a good understanding of how principal component analysis works. Now let's talk about principal component analysis. The goal of PCA is to reduce the number of variables in a data set without losing much information. Let's take a minute to think if this is even a possible feat. Now think about your favorite movie. The actors in the movie and the scenes in the movie are all three-dimensional and not flat, right? However, when you watch the movie on a screen, the scenes are projected onto a two-dimensional space, which is flat. Do you feel that you have lost much information about the movie by watching it on a two-dimensional space? Probably not. So this shows that it is possible to reduce the dimension of the data without losing much information. PCA is effective when we want to reduce the number of variables in the data set, but cannot completely eliminate any variables without losing important information. Now imagine that we are trying to show a spaceship traveling to the space in the movie. If we remove the distance dimension, then the spaceship would appear stationary on the screen. So what PCA does well is equivalent to removing the distance dimension, but still find a way to retain the depth information, so that the spaceship would appear to be traveling into the space. We will discuss how PCA does it in a minute. PCA is most effective if variables are measured using the same scale. This can be easily achieved through standardization techniques such as converting values into z-scores. PCA is also most effective if the variables are correlated. When variables are highly correlated with each other, PCA can achieve very significant reduction in data dimension without losing much information in the data at all. Finally, PCA works well when all variables involved are numeric. Although sometimes we can get away with converting categorical variables into dummy variables. For categorical variables, one can use the correspondence analysis, which is the version of PCA for categorical variables. These points here describe what PCA does. In the next few slides, I'm going to show you an example that illustrates these points so that you can see PCA in action. But let's first go over these key points about PCA. First, PCA transforms a large number of variables into a smaller number of uncorrelated new variables called principal components. You need to understand that the final product of PCA are no longer the original variables, but new variables called principal components. Hence the name principal component analysis. A smaller number of principal components will replace the large number of original variables, and this is how dimension reduction is achieved. At the same time, the new variables of principal components are uncorrelated. This is a very important attribute of the principal components. Lack of correlation between predictor variables means there is no overlap of information, which is a desirable attribute of a dataset. Second, principal components are representative variables that retain most, if not all, information that's in the original variables. This tells you that by replacing the original variables with principal components, we are not losing much information in the data. This triggers a couple of other questions. First, what is information in the dataset? And second, how do we know that we didn't lose much information when we converted the original variables into principal components? Well, these are great questions, and I'll answer these questions in the example later. Third, the values of the principal components are weighted linear combinations of the values of the original variables. Okay, the values of the principal components are produced based on the values of the original variables. Well, that is no surprise. One thing that PCA does is to provide us with the weights to be used in computing the principal component values from the original variable values. The weights are derived using a technique in linear algebra called eigendecomposition. That is why the weights are also referred to as eigenvectors. Eigendecomposition is beyond the scope of this class, so we won't discuss it here. However, eigendecomposition is performed by computer software in most cases, so you won't need to compute them yourself. Although these points may seem a little vague at this point, I'm going to show you an example now that will help crystallize everything for you.